Hello everyone, welcome to my channel. In today's video, we will walk through another sample problems on how to design the rectangular footing. And we will also cover the overall design process, focusing on the following key areas. Number one, how to determine the appropriate size of footing. The second is how to evaluate both one-way and two-way shear on the footing. The third one is how to calculate the longitudinal and transverse reinforcement. And the fourth one is we will discuss the common site mistakes related to footing design and how to avoid them, especially the details on the reinforcement. So let's dive on the problem. Here it is. Design a rectangular footing for an 18 inches square interior column with an dead load of 185 kips and a live load of 150 kips. Make the length of the long side equal to twice the width of the short side. We have the yield strength of steel 60,000 psi, the concrete strength of 4,000 psi. We are using the normal weight concrete, and the allowable soil bearing pressure is 4,000 psf. And the specific weight of soil, we have 100 pcf. This is pounds per cubic feet. Assume the base of the footing is 5 feet below the grade. So we have the foundation plan of the footing. We have the columns 18 inches by 18 inches. And let's get started with the solution. We have the section of footing. We have the depth of 2 feet and the 3 feet, the height of the soils. So we will check how we come up this dimension. So we assume that 24 inches footing with cover to from the cover to the center width of the steel. So 24 minus 4.5, that is effective depth of 19.5 inches. So we will calculate the effective soil bearing pressure, which is 4,000. We will remove the pressure due to the concrete and the overburden soil, the weight of the overburden soil. So we have 4,000 minus 24 over 12, because we convert it into feet, times 150 psf minus 3 feet, which is this one here, times 100 pcf, the specific weight of the soil. So that is equal to 3,400 psf or 3.4 ksf. So the required area is based on the service load, unfactored load. So that is 185 kips plus 150 kips. So the total of that, it will divide by 3.4 ksf. That is the effective allowable soil bearing pressure. That is equal to 98.5 square feet. So the area is equal to 2b times b, because we assume that the length is twice the width of the short side. So to simplify the equation, that is b is equal to the square root of 98.5, which is the area required, times 0.5. So we have 7.02 feet, or say width 7 feet. So twice the width, that is our length, which is 14 feet. So this is the area of the footing that we need to adapt, 98 square feet. So next is we have to calculate the ultimate factored soil bearing pressure, which is 1.2 times 185 kips plus 1.6 live load of 150 kips over 98 square feet, that is equal to 4.71. So this pressure is the ultimate, which is factored soil bearing pressure that we will use to determine the depth beam one-way shear and the punching shear, and also the reinforcement in both directions, long and transverse direction. So the next one is to check the depth of the footing for one-way shear. That is here. This is the plan of the footing. So we have the width of 7 feet and we have the 4.625. So this is the shear stress, shear force of the one-way shear. So continuing on determining the depth according to the ACI section 22.5, 0.5 and 0.1, we have this formula, and that is the VU, which is the shear force of the one-way shear, that is Hats here in the plan. So that is VU divided by P times 2, the square root of FC prime times the width of the footing. So we have to determine first the shear force VU, that is 7 times 4.625. So that is 4.625. Actually, this 4.625 is taken from 7 feet minus the 19.5 because the shear is taken from distance D from the face of the column. So we have here the depth. If we plug in all this value to that formula, we have 152,490 pounds over 0.75 times 1 lambda for normal weight concrete. There should be lambda here in the formula, times 2 times the square root of the concrete strength, which is 4,000 psi, times the 84. That is the width of the footing, 7 feet times 12, that is 84 inches. So equal to 19.14 inches. This is the required depth based on these equations for one-way shear. So the next one is to determine the total thickness of the footing. So we have a depth of 19.14 inches plus 4.5. That is from the bottom of the footing to the centroid of the steel bars. That is approximately 4.5 inches, and that is 23.64, or let's say 24 inches. That's why we come up the total depth of 2 feet. Then that we need to check the depth of the footing based on the two-way shear or punching shear. So first of all, we need to determine the parameter of the punching shear area. So 4 times 37.5 inches is equal to 150. So we can verify this one, that figure from this one here. So this is the foundation plan, two-way shear area. So the punching shear force is the Hats one. So we have to have this D is equal to VU over P times 4 times lambda times the square root of the concrete strength times the perimeter area of the punching area here. This is the perimeter. So to calculate the VU, so 98 square feet, which means we consider this whole area 7 times 14, that is 98 square feet, minus the area of this punching area here due to the column, that is D over 2. So if we calculate the total width of that area that is 18 inches plus 19.5, so that is the total one. So we have 37.5 inches, or equivalent to 3.125 feet. So we have here 3.125 square feet times 4.71. That is the ultimate strength of the ultimate factored soil bearing pressure. That is equal to 415.6 58. So this force is the total punching force of the hatch area. The next one is to, after plugging in all this value here in this formula, we have 415.58 kips over 0.75 times 4 times 1, that is lambda, square root of the strength of concrete, 4,000 times 150. This is the total perimeter area of this one here, the dotted one, is equal to 14.6 inches, which is less than to our assumed depth of 19.5. So generally, we are okay as what we have assumed depth. So there is another provision from the ACI code, section 22.6.5, that we need to check the depth based on these requirements. So we have the D equal to VU all over P times alpha D over BO, which is perimeter, plus 2. So times the lambda square root of FC prime times the BO. Here, the alpha is 40 for interior columns. This column can be considered as interior column because we have the perimeter is four-sided. So let's see if this columns is at the corner. So we have two-sided columns. We have different value of alpha. If it is on the side here, so if the columns happen at the side of the footing, we have three-sided alpha, that is different value also. So in our case, we use 40 for interior column. So plugging in all the value here, we have 415,580 pounds, which is this one here, over 0.75 times 40 times the depth over the perimeter here, plus 2 times the square root of 4,000, the strength of concrete, times the perimeter over the punching perimeter of this column here, that is equal to 8.11 inch, which is again less than to 19.5 inches deep that we have assumed. That's still okay for that two provisions from the ACI code requirement. Now the next one, we will calculate the longitudinal reinforcement, which is the reinforcement is from here going there. That's the longitudinal. That is our primary reinforcement because that is the moment where the moment, when we take the moment here, that is the biggest moment here compared to the transverse moment here. So let's proceed to determine the longitudinal steel. We will first calculate the lever arm. So from 14 inches, we will divide by 2. So 14 inches, the center of columns, divide by 2, that is 7 feet, minus 9 inches. So if we deduct that minus 9 inches, the lever arms is from this point, the face of the column, to the edge of the footing, which is equal to 6.25. So now we will calculate the moment. So if we recall the basic formula from the flexure formula, just like we used in beams, so we have this formula. Then if we find the steel ratio, then we have all these parameters, M and Rn. So if we determine the M and Rn, we can then calculate the steel ratio of steel reinforcement, which is rho. So now we will calculate the value of M. M is Fy over 0.85 FC prime, that is equal to 60,000 psi over 0.85 times 4,000 psi, the strength of concrete, and that would give us 17.65. So the next one is using B 7 feet or 84 inches, deep with a depth of 19.5 inches. We can calculate the Rn. So Rn is mu over P times BD squared. So if we substitute all those values in here, we have 643.9, which is the moment here, the moment from the face of the columns, times 12 times 1000, because we will convert this into inches to be consistent with our units, over 0.75 times 84 times 19.5. 84, that is the width of the footing, times the depth. So Rn is 922.54. So rho, we can calculate that rho based on this formula, or this one here, that is 1 over m 0.65, this one here, times 1 minus the square root of 1 minus 2 times 17.65 m. Rn is 322.74, which is this one, all over 60,000 psi. So the result of steel ratio rho is equal to 0.00566. So the area of the steel is rho BD, which is 0.00566 times 84 times the depth, and we will have that 9.27 square inch of steel. So if we use number 8 bars, that would give us a total of 12 pieces of bars, 12 pieces of number 8 bars. So that is the total requirements for the longitudinal reinforcement from here to there. That is 12 bars. So if we calculate that one, roughly 11 bars at 7 inches on centers. So that is the main bars. The next one is to calculate the lever arms in the short direction, the sign of steel in short direction, which means the reinforcement is going in that direction. So mu is equal to 2.75. 275 is from here, the face of column, to the outside of the footing. So we have 7 divided by 2, this one here, 4.5, minus 9 inches divided by 12, that is the half of the columns. So that would give us a 2.75. And that is the lever arms of our moment from here to there. So moment is 2.75 times 14 and times 4.71 KSF. So times 2.75 over 2, that would give us a 249.3. So we just take a moment from the face of the support from here to there. So the M, same what we have previously, M is equal to Fy over 0.85 Fc prime, that is 60,000 psi over 0.85 times 4,000, which would give us 17.65. So using B 14 inches, that is 168 inches, 14 feet is equal to 168 inches, and the depth of 19.5 inches. So if we calculate the Rn, that is 249.3 foot kips times 12 times 1000. So over P 0.75, the B is 168 inches, and the depth is 19.5 inches. So that is equal to 62.44. So if we plug all this value here in this formula, we will get the 1 over 17.65 times 1 minus the square root of 1 minus 2 times 17.65. Rn is 62.44 over 60,000 psi, so that would give us 0.001 So by inspection, the actual row steel ratio is too small. So the next one is to determine the minimum requirements of the steel bars. So we have the minimum requirements row from the ACI section 9.6.1.2. So we have rho is equal to 3 times the square root of fc prime over fy. So that is equal to 3 square root of the 4,000 psi over 60,000 psi. This is real strength of the steel bars, and that is equal to 0.00316. So there is another provision for minimum steel ratio. We have 200 over fy. That is equal to 200 over 60,000 psi, and that would give us 0.0033. So most of the time, this is the governing one, 0.0033. So that is the minimum reinforcement that we're gonna use in the transverse direction. So the area of the steel requirements in the transverse direction, that is 10.81 square inch. So if we use number 17, so it's about 18 pieces, number 17 bars in the transverse direction, which is from here going there, from here to there. So we will redistribute that one. Also the other one, we need to check the bandwidth requirements. So we have the bandwidth requirements because if we have the column here, there is a stress concentration on this area here, stress concentration, which is equal to the width reinforcement in bandwidth, that is over total reinforcement in short direction, that is 2 over beta plus 1. So beta is equal to L over B, and that is 14 over 7, that is 2. So if we substitute that value in here, that would give us 2/3. It's about 67%. So 67% of reinforcement required is 12 bars. That would be the number of bars that we need to provide in the bandwidth. Bandwidth is from here to there, that is equivalent to 7 feet. So for 18 bars, we will put here total number of 12 bars. Then we will redistribute the remaining one both sides. So here, take note, guys, that most common problems in the site is the arrangement of the reinforcement. So we have to take note that the main reinforcement here is always below the transverse reinforcement, because that is our main reinforcement, which is this one here. But sometimes they reverse this one. Instead of putting down, they put it above, which is not correct. So that is the common mistake in the site. So far, guys, this is the end of our video, and don't forget to subscribe or click like. If you have any question or comments, please comment down below. So thank you for watching. See you next time. Bye bye.